Hi and welcome to this talk about speculative dereferencing reviving Foreshadow. In this work we analyzed the address translation attack by Gruss et al., which was attributed to the prefetch instruction. This is wrong and turned out to be wrong, and we show that the actual root cause is speculative execution in the kernel. This misattribution led to wrong conclusions in follow-up work, for instance the Kaiser patch, and using the new insights we got from this new effect and the actual root cause, we present strong attacks like reviving Foreshadow. We also show how to leak values of registers within SGX enclaves and show how to trigger this effect in JavaScript. So to get an understanding how the address translation attack works, we need an understanding about attack primitives like the cache. So we have a latency between a cache hit and a cache miss, and this is illustrated as follows. If we access the variable a at first, it is a cache miss, and we need to perform a memory request, which then response loads the data into the cache, and after again accessing it, we have a cache hit. And the DRAM access is slow and the cache access is faster, and we can distinguish this timing difference, for instance, in attacks like Flush+Reload, where we have a shared memory between an attacking process and a victim process. And the thing is, since this is also physically shared, even though the virtual addresses are different, the one cache access for the victim process is also cached in the attacker side. So if the attacker performs now a flush onto the shared memory, it gets flushed out of the cache, and the victim later on accesses not a certain code location within the shared library, for instance. And after a certain time, the attacker would again access it. The attacker could recognize if the victim accessed it or if the victim did not access it. And this effect was used to spy, for instance, on key strokes or attack cryptographic primitives. Another important thing in the kernel, which is also used and required for the address translation attack, is the direct physical map, which maps the entire physical memory into the kernel. So each virtual address has a corresponding other address which maps to the same physical location. So the address translation attacks exploited this because it used the prefetch instruction to load kernel addresses into the cache, and by passing a direct physical map address, it was possible to see the corresponding address in the direct physical map for a certain user space address. And with this technique, you can basically translate a virtual address into a physical address. And the Kaiser patch was later on proposed to mitigate this address translation attack by unmapping the kernel when executing instructions within the user space. This is an illustration of the address translation attack. So we have this congruence between the variable I, or virtual address I, and its corresponding direct physical map address in the kernel. So first a flush is performed to flush out the variable I if accessed from the cache. Then the attacker performs a prefetch instruction with the direct physical map address. Afterwards performs a schedule. So this prefetching causes, or should have caused it to load the direct physical map address, or the physical address, into the cache. And after again accessing the virtual address, we observed a cache hit and could translate the address from the virtual address space into the physical address space. So we successfully reproduced the address translation attack, and then we only enabled the page table isolation and disabled all other mitigations for microarchitectural attacks. But for some reasons, still cache fetches occurred. This means even though the proposed mitigations were applied, the address translation attack still works, even with those active meltdown mitigations enabled. The root cause was attributed to the prefetch instruction, and what we first did was we disassembled this proof of concept and observed that, of course, to perform this prefetch, the direct physical map address has to be located somewhere in the register. So in the original POC, in the same similar system, it was in the register 14, for instance. And we also observed was that this additional scat yield seems to be kind of important to get a higher leakage rate, so more cache fetches per second. So what we then did was to enable all mitigations against all types of microarchitectural attacks, and suddenly the leakage disappeared. So as a next step, we knocked out all the prefetch instructions, but for some reasons cache fetches still occurred, meaning that it might have something to do with the value in the register, the direct physical map address. So we observed on a commodity system about 60 cache fetches per second. If we remove the scat yield, the leakage nearly disappeared. And then we systematically disabled or enabled the Spectre and MDS mitigations and observed if full Spectre variant 2 mitigations were applied, the leakage was completely gone. So what is speculative execution? So the CPU tries to predict the outcome of a certain branch, and depending on this prediction, parts of the code, true or false branch, get executed speculatively. If this prediction was correct, then the execution was very fast. If it's wrong, then the results are discarded. Problem with discarding the results is that there are still traces left in the microarchitectural components, for instance in the cache. The Spectre-BTB or variant 2 exploit works as follows, or it's Spectre-BTB works as follows. We have an array of mathematical functions, for instance, the function pointers for the sinus and cosinus function, and this function index which decides whether function 1 or 0, depending on the index is called, so either cosinus or sinus. So the sinus performs an additional lookup table data access, so it loads some data into the cache, and the cosinus does not. So at first run, it speculates that the cosinus function will be executed, but architecturally it executes the sinus function, which accesses the memory within this data area. On the next run, it speculates that the sinus function will be called, and also architecturally it will call it. So if we modify the function index to be 1, we observe that still the sinus function is called because of this branch target buffer, which decides or tries to predict which are the next branch targets. But architecturally the cosinus function is called, and we have now a speculative execution of the sinus function, even though we architecturally called the cosinus, and traces in this cache are left, and we could, for instance, use the Flush+Reload attack to recover, for instance, secret data within the cache. So we have speculative execution probably in the Linux kernel. So we debugged the kernel and found a Spectre-BTB gadget there. And it was since we called the schedule task, in the scheduling execution trace of the kernel, and we observed that this put pref task fair dereferences a user controlled register. And what we also observed was that this is not the only location where speculative dereferencing in the kernel happens. So we also observed that, for instance, for NVMe interrupts, so when performing the sync syscore multiple times, we observe that this also has a similar effect and leads to cache fetches. So bringing this all together, we have a POC which now looks like that. We fill all registers with direct physical map addresses. Afterwards, we perform an interrupt or a syscall, which leads to, in the code location somewhere, to an indirect jump. So depending on which handler will be predicted, for instance in this case we predict handler A, there will be a speculative dereference of the register RDX, and this will cause a cache fetch. Since we now understand the actual root cause, we can build up new and even more powerful attacks. Let's look at this Foreshadow L1TF attack. So it allows it to leak data which is resident in the L1 data cache, and this attack affects virtual machines, hypervisors, operating systems, or the system management mode. It was even demonstrated by Van Burg et al. That it is possible to read SGX protected memory or leak even the private attestation key. The root cause of this Foreshadow attack is located within a page table entry. So the present bit of a page defines whether a page is present in physical memory or not. So if, for instance, now a virtual machine is able to modify its page table entries, it could, for instance, try to clear the page table entry, or also a malicious user space application. So the thing with the L1TF, L1 terminal fault is as follows. If, for instance, the address is present, there occurs the guest physical address to host physical address translation, which performs an L1 lookup with the physical address if the data is in the L1, and then it would either go to the RAM or either looks up the data with the physical address in the L1. If the data is now not present, so if you access now a virtual address for which the relevant page table entry has the present bit cleared, then speculative or transient execution would ignore this invalid page table entry and still loads the reference data if it is present in the L1 data cache. So as it was still accessible, so we could leak data from the L1. So the basic idea of Foreshadow is then in a virtual machine, for instance, to modify the page table entry such that it points to a host physical virtual address. It could be the direct physical map address as previously explained. Then, since there arises an exception, we need to suppress it either using TSX or some proper exception handling, set jump for instance. And afterwards, since the data is encoded using a similar gadget like in BTB into the cache, we can perform a flush and reload. But the thing is with Foreshadow, it seems to be already mitigated. For instance, in Linux kernel virtual memory, the flush is conditionally, the cache L1 is, the addresses which are affected are conditionally flushed on context switch. And this is also the default setting for KVM. However, if we use now speculative dereferencing, we might be able to fetch data which is even in the L3, so data which is accessed on another physical core. But we could use, if we own, for instance, a core in our virtual machine, which is quite common, that we use one hyperthread to speculatively dereference the data and fetch it into our L1, and afterwards then perform the Foreshadow attack, accessing this data where the page table present bit is cleared and try to leak it via flush and reload. And this is possible, which we demonstrate in a minute. So summarizing this idea is like attack idea as follows: is we have this virtual machine which performs an interrupt or an hypercall. This could be, for instance, these NVMe interrupts containing the host physical address. So this is performed, then the hypervisor speculatively dereferences this address. Data is fetched into the cache. So for instance, in our case, then from L3 into L1, and then we perform foreshadow on this physical address and see whether we can leak the data. And here is a presentation where we have exactly this scenario explained. So conditional flushing is enabled. We start a victim program which constantly accesses this data array and runs on the core number 5. On the right we have this virtual machine, and we set the affinity such that only a single core, so 3 and 7, is assigned to both threads of the virtual machine. And as you can see, those two are siblings, so they're on the same physical core. Now the attacker would try to predict, but in this case we use the address. Now we perform interrupts and NVMe interrupts using stress -I and perform the foreshadow attack with the physical offset and leak a number of bytes. So slowly you can see byte by byte, or in this case 4-bit nibbles from the host, which are leaked from within the machine, even though active mitigations are So another use case of speculative dereferencing is the dereference trap, where we want to leak the content of registers from transient code paths. So the basic idea is we would require, of course, a Spectre gadget which would leak and dereference us our register data. But the basic idea is to ensure that the entire virtual address space of the application is mapped, and thus if this register would contain a secret which is speculatively dereferenced, the corresponding virtual address is cached. So for instance, if the value is 0x40,000 and we would map this, we would observe this cache hit if it is speculatively dereferenced. Exactly. The attacker detects then using flush and reload again whether a certain address was cached or not. So this can be used to leak register values in enclaves, for instance within SGX. So such a gadget could be, for instance, a jump table function pointer, or something related to polymorphisms, or a v-table, for instance. However, due to the address space limit, we are kind of limited. For instance, if we have performed flush and reload on every cache line, this would take like 2 days on a 4 GHz CPU. Instead, we map only virtual addresses to its own physical pages. We only map like 2 pages and focus on the 32-bit value range. So we map either on one half the page 1 and on the other half page 2. Using flush and reload, we then verify which one of those 2 halves was cached, and then using a kind of binary search approach, we can repeat this and make the range where the actual value is located smaller and smaller until a cache line granularity. And this looks illustrated as follows. So we have this speculative dereference of a register value, and this lies between one of those n mappings. And afterwards, so all these mappings map either to page 1 or page 2. We perform flush and reload and see in which of those 2 halves a cache hit occurs by probing a single address. And this can be repeated and allows it to leak up to a cache line granularity. So speculative dereferencing can also be triggered from JavaScript. So since we can also fill general purpose registers. For instance, if we use a large loop, we can fill quite a lot of the general purpose registers from V8 and also from SpiderMonkey. We observed that if we would directly trigger a syscall, that there would be like 20 cache fetches per second, and on an unmodified browser without performing any additional interrupts, we see about 2 cache fetches per hour. Using additional NVMe interrupts on the sibling, we observe that, like was performed in the L1TF attack, we observed that we can have up to 1 cache fetch per minute from an unmodified browser. How can this address translation attack be actually mitigated? We already mentioned it. So Kaiser itself does not prevent the address translation attack. What we also found is that the proposed eIBRS, which is a hardware replacement to the software side mitigation Redpoline, is also vulnerable. We observed about 30 bytes per second. If we have a gadget that in a kernel module, for instance, or in a kernel again, which speculatively accesses or dereferences a user space register again. Therefore, full Spectre-BTB mitigations, including Redpoline, are still required to prevent speculative dereferencing of registers in the kernel. And summing up this talk, the root cause of the prefetch effect was wrong, so address translation root cause was wrong. The real effect is speculative execution in the kernel. We showed where a potential or a large gadget is in the scheduling of the kernel. We, based on this new insights, demonstrated that L1TF mitigations alone are not sufficient to mitigate Foreshadow. We still need this Spectre v2 mitigations also enabled, which are quite costly. In addition, we showed a new technique to leak values from registers within SGX, and we demonstrated that prefetching, speculative dereferencing of registers can be triggered also in browsers. Thanks for watching this talk, and if you have questions about this, feel free to contact us.